Hello, I'm Ville Koskinen from Matrix Science. A new feature in Mascot Server 2.7 is the ability to identify cross-linked peptides from MSMS data. I'll show you how to use the new feature and discuss validating cross-linked search results. Crosslinks can be roughly divided into naturally occurring and artificially created. An example of a naturally occurring crosslink is the disulfide bond. In most experiments, disulfide bonds are of no interest, so they are cleaved with a reducing agent prior to analysis. But if the goal is to study protein folding, identifying the sites linked by a disulfide bond is crucial. Crosslinks can also be created artificially by a chemical reaction. A crosslink can only be formed between sites that are adjacent in a three-dimensional space. The maximum distance depends on the space arm length of the linker. So, the locations of the identified links can be used for constraining the three-dimensional shape of the molecule, which has obvious applications in elucidating protein tertiary structure, protein complex topology, conformational changes, and protein-protein interactions. Whether natural or artificial, a typical bottom-up crosslinking experiment starts by digesting the cross-linked proteins. This produces two types of precursor, linear peptides and cross-linked peptides. A linear peptide either doesn't span a linkable site, or if it does, the linker did not form a crosslink. Otherwise, the precursor is a cross-linked peptide, where an alpha peptide is linked with a beta peptide. The alpha peptide is conventionally the longer or more massive of the two. How cross-linked peptides appear to a search engine like Mascot depends on the type of the linker. Cleavable crosslinks are designed to be cleaved prior to analysis by various means like irradiation or CID. The link cleaves asymmetrically so that the alpha and beta peptides carry linker fragments with different mass. The fragment is modeled exactly like a variable modification on a linear peptide. The linear peptide matches are then paired up by a post-processing algorithm which figures out which peptides come from the same cross-linked precursor. Conversely, intact crosslinks survive MSMS analysis. There is additional complexity to the cross-linked spectrum. Alpha fragments that contain the linked site have a mass offset equal to the beta peptide mass plus the linker molecule, and vice versa for beta fragments. The search engine must be able to fragment cross-linked peptides in silico. However, the advantage is no post-processing step is needed. The boundary between cleavable and intact is a bit fuzzy. If the cleaving efficiency isn't 100%, there will be some precursors with an intact link. Similarly, an intact linker can fail to form a link, which leaves behind a linker fragment. Because of the great variety and complexity in cross-linking experiments, we've chosen an approach similar to quantitation. We want to keep the software universal and configurable and not tied to a specific experimental workflow. The crosslinking experiment in Mascot is modeled with a crosslinking method. The method defines which linker is used, which linkable sites are considered, linker directionality, what are the expected cross-linked products, and which protein or proteins are being linked. There are also a few filters available. There are four possible cross-linked products. An intralink is an intact cross-linked peptide within the same protein, while an interlink is an intact link between two different proteins. A loop link is an intact link within a peptide. Finally, monolinks model cleavable linker fragments, as well as dead-end or quenched links where only one end is attached to a peptide. I'll show examples of cross-linked products later. The standard search parameters like enzyme, fixed mods, and variable mods are applied to both linear peptides and cross-linked peptides. The link definitions are standard UniMod entries. Mascot 2.7 ships with 13 definitions, 7 for intact crosslinks and 6 for cleavable crosslinks. You can easily create your own definition for any link chemistry. I'll illustrate intact crosslinking with this dataset from the Merschler lab. The data is available as the Pride project PXD001538. The study uses a purified HOP2-MND1 complex from Arabidopsis thaliana, which is cross-linked using 3 different linkers. I've chosen the biological replicate 1 linked with disacchinimidyl superate, or DSS. DSS has 2 identical reactive groups, so it's homobifunctional. It's amine reactive and creates intact crosslinks between lysines and protein N-term. The study was designed so that there are only lysine-lysine links. The raw data was picked and processed in Mascot distiller. Cross-linked precursors often have a charge of 3+ or more, which means the product ions could also be highly charged. It's best to decharge the fragments by choosing to output fragment masses as Mh+. Setting up the cross-linking method is straightforward. DSS has a Unimod definition titled Xlink DSS, and we only want the K specificity for lysine-lysine links. The authors determined that only one of the 3 monolinks is possible, in this case the water-quenched 156 Dalton monolink. This has the code W in the Unimod definition. The accessions in the cross-linking method act as selectors and instruct Mascot to choose only the listed proteins for cross-linking. The sequences are in SwissProt, HOP2-Arath and MND1-Arath, so we can just list them here and select SwissProt as the search database when the search is submitted. The cross-linked products to consider are protein interlinking and intralinking and peptide loop linking. Finally, allow the beta peptide to be as short as 4 residues. If no min-len is specified, Mascot filters out alpha and beta peptides shorter than min-pep-len in search, which is 7 by default. The cross-linking method is a simple XML file, shown here. Monolinks are toggled in the MXM linker section. The MXM accession elements are the protein selectors, and these can optionally specify a database name. If there's no database name, Mascot chooses proteins for cross-linking by accession only, regardless of database. The scope and filters section contain simple key value parameters. The raw data has been picked, and we have a cross-linking method set up. The search is submitted as normal from distiller. Since the 2 proteins are in SwissProt, I've chosen to search SwissProt with athaliana taxonomy for convenience. Also remember to include a contaminants database. Choose the right cross-linking method in the search form. Once the search finishes, choose to open the full report in the browser. At the moment, the distiller can only display linear peptides. Support for cross-linked matches will be added in a future release. The protein family summary report has been extended to display cross-linked search results. The modification statistics table gives counts of discovered intact links, monolinks and loop links. Xlink DSSW on the first row is the 156 Dalton monolink enabled in the cross-linking method. The crosslink and loop link rows display the intact linker mass as well as the linked sites. Protein inference is not affected by interlinking. Because HOP2-Arath and MND1-Arath don't share any significant peptide matches, protein inference puts them in different families, regardless of whether there are any interlinked peptide matches. Notice also the small amounts of evidence for other Arabidopsis proteins in the sample, despite the high levels of purification. Expand the first protein hit, HOP2-Arath. The peptide match table displays cross-linking data in a compact form, and I've selected a few example rows here. On the first line is a loop-linked peptide. A loop link is an intact link between two residues in the same peptide. Here the link is between lysines K17 and K20. Loop links use the symbol ~I to indicate it's an intact link. The next two rows show matches to the same peptide sequence, this time with the W monolink. Monolinks are variable modifications generated from the linker definition. With cleavable linkers, this is usually the only cross-linked product of interest, since monolinks represent the linker fragments. Monolinks can also be used for modeling dead-end or quenched links, such as the water-quenched monolink here. Further down, there are three matches with an intact crosslink. The first two are protein intralinks, which means it's an intact link between two non-overlapping peptides within a single protein. The last line shows a match to a protein interlink. An interlink is an intact link between two peptides from different proteins. The alpha peptide is in MND1 areth and the beta peptide in HOP2 areth. The scores for all the matches are standard Mascot scores, and the identity and homology thresholds are calculated using the same statistical model as for linear peptide matches. Which of the matches on the previous slide are correct? The usual approach is to do a target decoy search, which allows you to estimate the false discovery rate. This approach works if you're using a cleavable linker. The linker fragment is just a variable modification, and all the peptide matches are ordinary linear peptides, so standard FDR estimation techniques work well in this case. However, when you're using intact linkers, the search space is often too small for a meaningful estimate of the FDR. In the present case, the sample is expected to contain only the two purified proteins. If you set up a two-sequence database and search 10,000 MSMS spectra against it, no statistical model can give a meaningful estimate of the FDR. In this case, I've used as the target database the 15,000 A-Thaliana proteins in SwissProt, plus a couple hundred contaminant sequences, which allows incorrect matches to distribute a bit more evenly. Even so, the peptide matches completely saturate the available peptide sequences from the two target proteins, and there are few matches in other proteins. The Mascot statistical model is robust and will give you reasonable separation between correct and incorrect matches, even in these adverse conditions. Nonetheless, it's prudent to keep a skeptical mind. Let's look at a few example spectra. Here's a peptide-view report of a cross-linked match with excellent fragmentation from both alpha and beta. The score is 74. Further down the page, there is a fragmentation table for the alpha peptide and another for the beta peptide. The fragment masses have no overlap between the two, which shows both peptides have independent evidence. At the bottom of the page, you can see the query also matches a slightly different beta peptide. However, the rank 2 score is much lower, and there is no ambiguity in the alpha peptide, so we can be confident the top match is the correct match. Here is another cross-linked peptide match with a high score and pretty nice fragmentation. At such a high score, 105, it looks very promising, but I have to dash your hopes. Here are the matches at the other ranks. It turns out beta and alpha are sequential in the protein sequence. The concatenated beta-alpha sequence with a water-quenched monolink has exactly the same score and equally convincing fragment matches. The location of the potential monolink and crosslink is also in question. The MSMS spectrum has no evidence to differentiate between the alternatives, so choosing the correct match requires consulting structural data. This also shows the importance of presenting an integrated report. If the search engine matched only cross-linked or only linear peptides, the ambiguity could be easily missed. Here's a cross-linked match where the identity of the beta peptide should be questioned. The alpha peptide has a nice sequence ladder, but there's no fragmentation from the beta. There's an almost as good a match at rank 5, where the beta peptide is completely different. The alternatives score almost the same, because there are no alpha fragments that span the linker site. The two alpha fragments match exactly the same observed fragments. Finally, this cross-linked match is very similar to the previous one, with no fragmentation from the beta peptide. But in this case, the search space has no other alternative for beta. If we assume the search space is complete, there's no reason to doubt the identity of the beta peptide, even if there are no beta fragments in the spectrum. Other common ways to validate intact cross-linked matches is by comparing with existing annotations and comparing with structural data. If the proposed crosslink would have a length longer than the linker's spacer arms, it's either a false positive or the structural data is incorrect. Mascot doesn't currently make use of structural data, so the validation must be done with external tools. One way to visualize the results is by viewing them in xiVIEW. This is a search engine independent tool maintained by the Rapsilber laboratory. Export the search results in xiVIEW CSV format from the Mascot export form. If you want to view the annotated spectra in xiVIEW, also export the peak lists as MGF. And finally, export the sequences as FASTA. xiVIEW can fetch the protein sequences and structural data automatically, but unfortunately the default accession format for SwissProt in Mascot is the AC format, and xiVIEW expects the raw accession. And now upload the files to xiview.org. Here's an example circular plot of the crosslinks between the two proteins based on the Mascot search data. xiVIEW can also plot histograms like this one, showing the cross-linked match charge states. As expected, nearly all of the cross-linked matches have charge 3+ or higher. Unfortunately, there is currently no crystallography data for the HOP2-MND1 complex from Arabidopsis thaliana, so I can't show you the 3D view. The xiVIEW CSV format is a simple tabular format, which you can load in Excel or LibreOffice. Modifications like oxidation are encoded as delta masses within the peptide sequence. The CSV file can be edited before uploading to xiVIEW, for example if you want to remove a putative crosslink because it fails a quality check. xiVIEW can also read crosslink data in MZ-IdentML 1.2 format, which we will support in a future release of Mascot. If you'd like to see more examples of cross-linked searches, we have some on our website. Thank you for your attention.